topic from the crystal field theory, and this topic is from complex compounds. In this first, I am going to discuss about in this crystal field theory. I am going to explain about postulates of CFT. First point, postulates of CFT, and then applications of the CFT in octahedral complexes and tetrahedral complexes. These two are the topics which I am going to deal now. So, moving on to the crystal field theory, and who proposed this theory? This theory was proposed by Vleck and Bleeth. These two are the people who proposed this theory, and they explained very well about this CFT, and they are able to explain about the structure of the molecules, magnetic properties, color of the compounds, and along with that they were able to successfully explain about the everything in detail compared to the VBT. Now I am going to discuss about the postulates of the VBT. So these postulates, what are these postulates? So postulates are the assumptions which proposed by these two scientists about crystal field theory in this CFT, right? And what are these postulates? First postulate, they have assumed the bond between metal and ligand as purely ionic. So before entering to this particular postulates, we must know what is my metal and what is ligand. Metal is the one which has a tendency to accept lone pair of electrons. It accepts lone pair of electrons, due to which it is going to have a vacant orbital. Due to this vacant orbital only, it will have a tendency to accept electron pair from the ligand. And what is ligand? It is a electron pair donor. So electron pair donor is ligand and electron pair acceptor is metal here. So according to their postulates, they have explained that the bond between metal and ligand is purely ionic. That means they have explained this particular interaction as electrostatic interaction. As this is going to be electrostatic interaction, the bond between them is going to be ionic. Moving on to the second point, they have considered ligand, that is negatively charged ligand, as point charge, whereas neutral ligand they have considered as dipole. So by considering these two, that means the nature of the ligand as negative and neutral. By considering these two, we can assume that the bond between metal and ligand can be ion interactions or metal between metal and this dipole. That means ion dipole interaction. So what it means? They have considered this ligand as a positive point charge or dipole. Based on this, the interaction between metal and ligand can be ion-ion or ion dipole interactions. Moving on to third point. For here, we are going to consider about d-orbitals. So we all know that d-orbitals are of 5 d-orbitals. These 5 d-orbitals, how they are going to arrange around the axis, we all know very well, that I am going to show here. There are 5 d-orbitals in which one dxy, other one dyz, other one dzx. These three are the, this is not going to come under postulate, but we must know about these d orbitals, 5 d orbitals, so how they are going to arrange in the around the axis. This dxy, dyz and dzx are 3 orbitals in which these are arranged between the axis. That means between x and y axis, these are arranged like this. In case of y, same way we can imagine this as y and this as z. Between y and z, the d orbital is like this. Same way between z and x, the d orbital is like this. So these are three three d orbitals out of that 5. These 3 d orbitals in which the orbitals are arranged between the axes. Now we are going to see 2 more d orbitals here. I am going to write here. One is dx square minus y square. That means one is x axis, other one is y axis. This dx square minus y square in which the orbital lies on the axis, whereas dz square, this is also going to lie on the axis. For example, if I am taking as z axis, then z square is going to be like this. So these are 5 d orbitals. From this one, first itself, before going to these postulates, we should know all these structures, because the structures play an important role in the octahedral and tetrahedral application part. That is why I have shown this dxy, dyz, dzx, dx square minus y square, dz square here. In this one, what to note here is very clear. These 3 are the orbitals which are having lobes between the axes. These 2 are the orbitals which are having lobes on the axis. This is on the axis. These 3 are between the axis. This point to be noted here. In our third point, we have seen just now what is the structure of these d orbitals. So that's our third point. The third postulate is going to start now. These d5, these all 5 orbitals, are going to have same energy. That is what the postulates which given from the CFT. The third point is this all 5 orbitals is going to have same energy, and hence they are going to be called as degenerate orbitals. They are going to be called as degenerate orbitals. Degenerate orbitals. What is degenerate orbitals? Degenerate orbitals are the orbitals which are having same energy. That is what the third postulate. Now fourth postulate. In this we are going to see the complex formation. During complex formation, what is going to happen? That is what this postulate is going to explain us. It's fourth postulate. During complex formation, what happens? The ligand will have a tendency to donate lone pair of electrons to the metal, right? So during the formation of complex, when the ligand is approaching the metal ion, the ligand is going to approach the metal ion here. When the ligand is approaching the metal ion, it approaches spherically. In this direction, it will approach spherically. So during this approach, what happens? The repulsions arises between what? Between ligand electrons, and already metal will have some electrons, right? Metal will have electrons inside. Even though it's having empty orbital, metal will have some electrons. So there will be a repulsion between the electrons of the metal and the electrons of the ligand. Due to this repulsions, what is going to happen, that we are going to see in the fifth point. So during complex formation, the ligand approaches the metal ion, and during the approach of the ligand to the metal ion, there will be a repulsion between metal and ligand. Due to this repulsion, what happens? That is going to be explained in the fifth point. Due to this repulsion, what is going to happen? First, all 5 orbitals These are dxy, dyz, dzx, dx square minus y square, dz square. All these 5 orbitals going to have same energy. When the ligand approaches the metal ion, what happens? The energy rises. The energy rises. But it will not split now because the energy just raised. Why it's energy raised? Because of the repulsion. So the energy raised, and here there will be a path called barycenter. This energy will consider it as 0. Here we will take this center as barycenter. From this barycenter, it is going to undergo splitting. This splitting is based on the octahedral and tetrahedral complexes. This splitting is based on the number of ligands approaching it and how the ligands are approaching it. Based on this one, we are going to explain about octahedral complexes, tetrahedral complexes and square planar complexes, which is there in the syllabus. Now, I am going to explain you the sixth point. What is sixth point? So, this splitting is going to happen. So, in how many ways the ligand can approach? One point. And in how many ligands can approach? How many ways the ligand can approach and how many ligands can approach? So, based on the number of ligands, these complex compounds can be octahedral. That means the ligands are 6 here. The metal will be approached by 6 ligands and it's going to be called as octahedral complex. For example, if the metal is approaching ligand in this fashion, then it is going to be called as tetrahedral. So, here 4 ligands are going to approach here. It can be tetrahedral or it can be square planar. It depends upon the nature of the ligand, because in both the cases the ligands are 4 only. In this case it is going to be tetrahedral, in this case is square planar. Moving on to other shape. What else shapes are possible? In this case, the ligand approaches the metal ion from 5 directions, and so it is called as trigonal bipyramidal. Trigonal bipyramidal. Right? And these are the some of the examples in which this have different structure of complex compounds. Now we are going to discuss about applications of CFT in octahedral complexes.